Okay, today's third and next lectures. When I come to this class, do you know what I really want for this class? I really hope I can see more smiles or in more laughters. And in addition, more positive energy, more enthusiasm, okay? A pleasant atmosphere, okay? Okay. As I said again and again, learning in English is tough, okay, especially for us, okay? I think for Asians, English is a difficult language because when I was in the United States, when I was a graduate student, I think Taiwanese students, I'm one of them, speak full English. And Korea and Japanese students also speak full English. But in comparison, students from Europe, relatively speaking, speak good English. I think it's probably have to do something with the basic structure of our language. But nevertheless, okay, learning English opened many doors for us because, for example, when you're listening to a sound written in Mandarin compared to some written, I wouldn't say English, written in Taiwanese dialect, they are not the same. They are not the same. They give you different kind of feelings, different type of vibrance, okay? Different types of gut reactions. I don't know how to describe them, but they are not the same. Both of Psalms, you will have medical Psalms which was written in Taiwanese or Mandarins, okay? And they are all very good, but they are good in a different ways. So by understanding Taiwanese as well as Mandarins, I have a broader channel of accepting the good things of this world than people who only understand Mandarin. Same thing happened here. If I understand English, if I have a very good command of English, I open not just one door, probably many doors for this world. For me to understand the good things, the beautiful things surrounding us, including knowledge, including cultures. All right. So, as I said it again and again in this class, learning English is hard. In that regard, I want to pay my respect to all of you who chose this curriculum. All right. You knew that when you're entering this program that you'll be learning in the entire college time in English, and you accepted this challenge, okay? No matter how it turned out, no matter how you feel today, my admiration for your choices is very solid and very true. Okay, I probably didn't have. If I go back to my teenage years, go back to the time when I was in the age of choosing a college program, I probably wouldn't have the same courage as you had. Okay, so that is really something. All right, let's switch to a new topic: time frequency domain analysis. What do we want to do here? Now, when we study a control system, we can study the control system from time domain. we can also study the control system from frequency domains. What I want to do here is to relate time domain results with frequency domain results. So something happened in a time domain, I can expect what will happen in the frequency domain and vice versa. All right. Now, we also these two equations before. It represents the importance of system spectrum. All right. How system, the transfunction of system, revise the amplitude and phase spectrum of the input to form the new spectrum, new amplitude spectrum, and the phase spectrum at the output end. We also that. Now, in a simple, if I in a simpler case, in a very simple case, what I have is a sinusoidal input, and the steady state response of this system will look something like this. Remember, the input and output frequency will always be the same, provided that the transfer function that we are dealing with is a time-invariant linear system. However, the amplitude and the phase will be altered by the system, all right? By how much? It depends on the magnitude spectrum as well as the phase spectrum of the system, okay? This is an important slide. I hope you learn it by heart. Now, we also did slide before. This is a plot of the frequency response of a loudspeakers, okay? Now, to measure loudspeakers frequency response, what we do is we play a non-text signal. Most commonly a sine wave, that is a sinusoidal signal with varied frequencies. For example, I can go from 10 hertz to 20 hertz to 30 hertz and all the way up to, for example, 20 kHz, all right? Now into the speaker and record the sound produced by this loudspeaker with a calibrated microphone in the reflection-free setup, okay? So what I measure is the sound produced directly from the loudspeaker, not sound reflected from the wall on any surrounding background, all right? And compute the sound pressure level, which is denoted as SPL versus frequency, okay, using measurement software. So this is the frequency response. As I said before, different loudspeakers have different frequency response. And as I said before, for bookshelf loudspeaker or most loudspeakers, it is relatively incapable in reproducing bass due to the size limitation of the loudspeakers. Now, the first thing I want to address in this in this part of the lecture is the concept of bandwidth. All right. Now, we also this picture before. For this such a plot, there is one critical parameter, which is what we call cutoff frequency. All right. In control system, bandwidth refer to the frequency range over which a control system can effectively respond to input signals. All right. So if I go to the loudspeaker, the bandwidth is probably this region, right? Because why do I take this? What isn't this frequency region a part of the bandwidth? Because in the frequency is in this region cannot be faithfully reproduced. Why? Because the SPL value is just not large enough. Therefore, the sound it produces is almost unhearable for our hearing system. All right. So in that regard, this stuff, okay. So this is the true idea behind bandwidth. Okay. the frequency range, the frequency band over which a control system can effectively respond to input signals. All right? Now, in frequency domain analysis, the bandwidth of a closed-loop system is usually defined as the range of frequencies, usually from 0 up to some cutoff, where the magnitude of the closed-loop transfer function remain about a certain level. For example, 3 dB, all right? So this is a common definition of bandwidth, but this definition has one assumption, that is, in the very low frequency region, for example, omega equals 0, okay? This output of the system is approximately 0 dB. And this assumption is true for many mechanical as well as electrical and electronic systems, okay? But it is not always true. One distinct example is this loudspeaker, all right? So this curve only gives you a general idea of bandwidth, but it is not a mathematically accurate definition of bandwidth, all right? Because the true definition, the true idea of bandwidth is the frequency range where a control system can effectively respond to the input signal. And there is no guarantee a control system can always effectively respond to the input when the input signal has very, very low frequency components. All right? Now, but nevertheless, you have to understand this is a common definition, okay? Which means here we have minus 3 dB, and it means the output is about 70.7% of its input. Now, why 0.707? Because 0.707 is equal to 1/2 square root. Why 1/2 square root? Because if you take the square of 1/2 square root, it gives you 2. Why do I want to take square? Because when it comes to the energy or the power of the signal, you always take square. So at this level, it means half of the power of the energy cannot be maintained, cannot be preserved, okay? At that frequency, and because outside the bandwidth, outside the bandwidth of the frequency, outside the frequency range of the bandwidth, this output of the systems, when it comes to energy, can only maintain about 50% or less of the original input. All right? Now, as I said in the beginning of this hour's lecture, we want to relate frequency domain measures with time domain measures. So here, with first order system as an example, we want to study the relationship between pole, bandwidth, and speed of response of first order system. Speed of response, it of course can be measured by, for example, settling time, peak time, rise time. So it's pretty much a time domain measures. Bandwidth is of course by definition a frequency domain measure. And pole, we all know it's come from X-plane, all right? Now, remember, let me review this again, all right? Whenever you have a transfer function, remember, it's a function of frequency, okay? And remember, it's a complex function, which means as a function, it not only has its own independent variable, and its function, the value of that function actually consists of two parts, the real part and the imaginary part. So to understand the dynamics, to truly understand, to truly investigate transfer function, you have to go to complex plane, which is a 2D space, all right? And in this complex plane, the real part related to the horizontal axis relate to the real part. The horizontal axis relate to the real part, and the vertical axis correspond to the imaginary part. But for frequency domain analysis, in studying control systems, we prefer polar coordinate representation, right? And by going through this simple mathematical derivation, we know that such a function of frequency can be represented by its polar coordinates, okay? Because this is the magnitude and this is the phase of this transfer function, all right? Okay, now to determine its magnitude, you can use this equality. To determine its angle, you can use this equality, okay? We also seen this, we have seen this before, okay? What I'm doing here is just review it again because it doesn't seem so natural. Because why does it doesn't seem so natural? Because everything are presented in with complex numbers, and complex numbers just doesn't seem real, because as I said before many times, in the real physical world, no physical variables and have complex numbers. Okay, all physical variables have real numbers and real numbers only. Okay, we also this slide before. This shows how we set up asymptotics for first order system. Okay, now this family of curves represents the state response of a first order systems, which is this. All right, now P here is the time constant of the system. As you saw this before, okay? But as you can see in this figure clearly show you that the smaller the time constant, the faster the system. All right. Now what we want to do is relate the frequency domain measures with. I'm sorry. Let me put it like address my statement again. Here, what we want to do is relate this, and this, okay? Pole, bandwidth, and speed of response. All right? Now, this curve tells us a smaller time constant indicate a faster response, okay? So the time constant is therefore often considered when designing a controller to ensure appropriate system performance. That is why time constant is important, because it is almost like a golden measures, which can be used to characterize the speed response of the system, and especially a first order system. Now, this is a transfer function of a first order system whose time constant is tau 1, all right? Now, this is its phase plot. This is the asymptotics of its magnitude plots. As you can see, the break frequency or the corner frequency here is 1 over tau 1. Okay, so the bandwidth of the system, where is the pole located? The pole is located at this particular location. Okay, right? So the smaller the time constant, the fast the system, that's for sure. And the smaller the time constant, the further away the pole is from the imaginary axis. All right? And let me go one step further. The smaller the tau 1, the larger the bandwidth of the system. Let's say tau 1 is 1, okay? If tau 1 is 1, then this value is 1, okay? Let's say tau 1 now become 0.50, which means I have a smaller constant, which means the pole, the location of the pole shifted from -1 when tau is equal to 1 to, to -2. And when the time constant reduces from 1, reduces from, what's the matter with me? Okay, reduces from 1 to 0.05, okay? Then the corner frequency shifted to, from 1, I'm such a poor drawer. Okay. Okay. Here, all right, where this corner frequency is now 2, which means I have a large bandwidth. Because if I use the conventional definition of bandwidth, what I have is I need to draw a line which from the -3, I need to draw a line -3D line horizontally across the entire frequency range and determine the corresponding bandwidth, right? So apparently reducing the time constant increase the bandwidth, all right? So this figure demonstrates that bandwidth of first order system is controlled by the pole location, all right? The break frequency occurred at this omega equal to 1 over tau. Remember, tau is the time constant, where the magnitudes begin to drop at -20 decibel per decade, okay? Which means whenever the frequency, the value of the frequency is increased by 10-fold, the decibel value decreases by 20 dB, okay, by 20. A pole closer to the imaginary axis, which means this will be smaller, and hence large time constant. And the system will become slower. The speed of response of the system will become smaller because it will have, in such a case, a larger time constant and produce a narrow bandwidth, okay? And vice versa, okay? So let's look at some examples. Here I have two systems, okay? Both of them are first order system. This system has a time constant of 1. This system has time constant of 3. So we expect this system to be slower, and that is exactly what we have here. If you look at the step response of these two systems, apparently system 2 has much slower step response when compared to system 1. And this is only for step response. When you see, how do I call this? When you need to track a linear output, okay? Again, system 2 is much smaller, much slower than system 1. And this plot shows the bandwidth of these two systems. Apparently, system 1, since it has a smaller time constant, Therefore, it has a larger bandwidth. All right. So the conclusion here is a larger bandwidth means system can pass wider range of frequency, including higher frequency components. Why systems have larger bandwidth can have faster response? The answer is that if a system have larger bandwidth, that means it can pass wider range of frequency, including the high frequency components. That is, it will effectively respond to the high frequency components of the input signal. So the input, if the input moves very, very fast, if system with a larger bandwidth is more capable in catching up with the changing input because it will reflect in the output end of the system the change made by the input, because high frequency components of the input can be effectively reflected at the output end of the system. Okay, a faster step response, which means a system with higher speed of response, requires the system to process the high frequency content of the input step function very quickly. If the input changes rapidly and my system cannot effectively respond to those changes, then my system is a very slow system. That's what this statement, that is the message this statement what one wants to pass to us. Therefore, large bandwidth means high speed of response. Okay. Now, so increasing bandwidth usually improve tracking ability and can reduce stability margins. All right, we will including phase margin and gain margin. Why is that the case? Okay, before answering that question, let's look at another example. Okay, again, here I have two first order systems. One with a time constant 1 and one with a time constant 5. This is expected to be a slower system, and this is exactly what we have. System 2 has a slower step response, and here also system 2 has a smaller bandwidth. Okay, so if a system have a larger bandwidth, okay, that means a system will have, let me put it this way, okay. Let's say originally, this is my system, okay. Let's increase its bandwidth. I'm sorry, to this. All right. I don't need to draw them by myself. Okay. Do I? Yeah, probably I need to do that. Okay. Now, then this is, I'm sorry. This is the phase response. And this is minus 180 degrees. All right. And it looks something like this. All right. If this is the case, then originally my gain crossover frequency is here. So this is my phase margin. But by increasing the bandwidth, my gain crossover frequency become higher, and the phase margin become smaller. So the price we need to pay for the higher speed of response due to larger bandwidth is I have smaller phase margin, which means speed of response and relative stability are trade-off that we need to balance. Okay, if we want a system to be fast, then probably what we need to do is we have to sacrifice relative stability, okay? And that also means if I want to have larger stability, relative stability, I have larger robustness for my system, then I probably need to reduce the bandwidth of the system, which means I probably had to sacrifice, I need to compromise, make some compromise on the speed response of the system. Okay, that is the trade-off. All right. Now, increasing the bandwidth also have another side effect. Okay, a higher bandwidth will also pass more measurement noise, which often resides at a higher frequency. So the problem of high frequency noise is it can reflect the impacts of high frequency components of the input signals. But the inputs come from everywhere, including the nominal input that we planned for our control system, and including unwanted input, which will come from disturbances and measurement noise. So high bandwidth improved tracking made the system more sensitive, but at the same time also make the system more sensitive to noise. So what is the practical rule of thumb in designing or in specifying the desired bandwidth for our closed-loop system? Bandwidth is often taken as approximate upper bound on the frequency of the input the system can track with small steady-state error. To determine the bandwidth for our control system, the first thing we need to do is to understand our input. What kind of inputs we need to consider, we need to process, we need to deal with. And for those inputs, what is the highest frequency components of those input signals? Okay, so if the input signals, the highest frequency component of the input signal is never larger than 100 hertz, then there is no need for my control system to have a bandwidth larger than 100 hertz, because any frequency component higher that is higher than 100 hertz are not supposed to appear in the input end of my system, right? So if it never appear, then my system do not have to prepare for it. All right. Okay. Those results, the discussions that we just had are for first order system. Now let's still discuss the same issue. That is, we still want to know the interactions between pulse, bandwidth, and speed of response of the system. But the focus now switch from first order system to second order systems. All right. Now, again, here, based on the definition of bandwidth, we want to determine what exactly the cutoff frequency is. All right. That is, our common definition for bandwidth is this minus 3 dB points, and this omega b represent the cutoff frequency, or simply the bandwidth of the system. Okay. Now, what I want to do next is to determine omega b for a second order system, and I want to determine omega b in such a way that it can be represented as a function of natural frequency and damping ratio, because as we seen before, damping ratio and natural frequency are the two most important parameters for second order systems. Okay, so this is the transfer function of a standard second order system. All right, now at the bandwidth, okay, or the cutoff frequency, this has to be true. That is, the ratio between the of the output to the input when it comes to magnitude has to be 0.707. Okay. Now, if this is true, okay, then this has to be true. Okay. What I do that is just take the magnitude of this and put it here. All right. This has to be true. And since I don't like this square root, so I square everything. Okay, and this is what I have. All right. Now remember here 707 is 1 over square root 2. If you square it, it's 1 over half, 1 over 2. Okay, and half, which is 0.5. Okay. Now, if I multiply this with this, and I square it, this is what I have. Okay. Now it has to be equal to the square of omega n squared, which turn out to be omega n to 4. Okay. Now remember, my job here is to determine the bandwidth, omega b. To do that, what I do is simply multiply, divide everything by omega n squared, and that's, but I'm sorry, omega n to 4. Okay, and this is what I will get. So by treating this as x, all right, by treating this as x, I can convert this polynomial into a second order polynomial. Okay, where x is simply this, and then I can solve it, and this is what I will get. Okay, so finally, I come out with this final results, which tell me the bandwidth can be determined, which tell us how bandwidth is related to natural frequency and damping ratio. Okay, so another way to look at it is I simply divide both sides by omega n, all right? And I just plot them out as a curve, as a function of eta, okay? And this is what I get. Now, from this solid blue dark, from this black curve, as you can see, when eta increases, bandwidth actually decreases, right? The larger the damping ratio is, the smaller the bandwidth. The relationship is monotonic, okay? Does that make sense? Yes, it makes sense, because damping ratio corresponds to stability. Omega b bandwidth corresponds to speed of response. There is a trade-off between these two critical factors. All right. So if by increasing the value of eta, we have better stability, but that results in smaller bandwidth, which means the speed of response of the system is now slower. All right. So and for this part of curve, okay, when eta is between, let's say, 0.3 and 0.8, this curve can actually have a very good linear approximation. Well, the equation of that approximation is this. From here, you can also see that increasing eta reduces bandwidth. Okay, the relationship between them is negative. They are negatively correlated. Okay, not positively correlated. Okay, that is what we have had before. But if you remember the definition of settling time and peak time, then this equality can be rewritten as this or this. What does it what does these two equations tell us? It tells us that the settling time is actually inversely proportional to the bandwidth, okay? And settling time is what? It's the time that that required for the state response of a second order system to enter a settable region, okay? For example, minus positive 2% of the desired output, all right? And we all know what peak time is. For state response, peak time represents the time when the system reaches the top of its response. In any regard, this represents the speed of the system. The smaller the TS and TP, the faster the system. And this tells us when it is smaller, then this is larger, okay? And this is the reason why we think bandwidth is a very good measure to characterize or to quantify the speed response of the system, all right? Now, so bandwidth is, in my opinion, actually is a very general and very good measures to characterize the speed response of the system. Of course, you can use settling time and peak time to characterize the speed response of the system. But remember, where do these two terms come from? For our derivations, it comes from standard second order system. And based on the unit step response, we can specify TS and TP. And TS and TP in this regard is only good for second order system. So TS and TP, settling time, peak time, has some limitations. Okay, apparently they are very good for second order system, but for third order system, for even high order systems, we are not so sure. But bandwidth is a different story. Bandwidth, its definition comes from the frequency domain. All right, it has not imposed any assumption regarding to the order of the system. It just identify the frequency rate, the frequency band where the input signal can effectively respond, be taken care of by the system. So the impacts of the input can be faithfully reflected at the output end. All right, it just identifies those work frequency band. So it has not imposed any assumption regarding to the system order. So in that regard, you can see bandwidth is actually a great measure for speed response of the system. All right. Now, one problem of the common definition of bandwidth is that typically we assume bandwidth to be the frequency at which the closed loop gain drop by 3 dB. Okay, but if you look at our second order system and you apply that definition, what does it tell us? What does it tell you? It tells you that, let's say this is, minus 3 dB. All right, and you draw a line horizontally across the frequency. And then, for example, this is one bandwidth. This is the bandwidth. Okay. However, this is not a good definition. The bandwidth calculation derived from the minus 3 dB definition is still mathematically correct, but its interpretation as a meaningful performance metrics for very lightly damped system become questionable. All right. Why does it become questionable? Because if you think of this is the bandwidth, okay, then we will run into a problem when our input signal enter this region, because in this region, the problem is that it's not that the output will not reflect the impacts of the input. It is that it will reflect the impact of the input. It will respond to the input, but the response is simply too large, too dramatic, and therefore undesirable. All right, because the response is dominated by the resonant peak, and we don't like resonant peak. All right. Now, so for lightly damped systems, generally speaking, it can be mathematically shown that the effective bandwidth, effective frequency bands, is approximately 2 eta omega n. Okay, note that the poles for second order systems are located at here. Okay, I'm sorry, this is under natural frequency, and I should have a J here. Okay, so that this becomes an imaginary part of the poles of the complex conjugate poles of the second order system. So the bandwidth in this case for lightly damped system is actually twice the distance of the location of the poles to the imaginary axis. All right, because this so-called -3 dB definition for bandwidth is interpretation is questionable, okay, and actually not applicable in real applications. Okay, keep that in mind. All right. Now remember that from this figure, it tells us smaller damping ratio, larger damping ratio means smaller bandwidth. Okay, so here I have a family of curves. Okay, there are state response of second order system, but with different damping ratio. The smaller the damping ratio, the faster the system. Why does it have? Why is that the case? Because smaller damping ratio, larger bandwidth, faster response. Right? In contrast, if bandwidth is smaller, then the damping ratio is larger, then the speed response is smaller. All right, let's look at another examples to demonstrate the impacts of bandwidth. Here I have two second order systems. Their damping ratio are all 0.05. They have the same damping ratio, which is 0.05. But in this case, the natural frequency is 10. Okay, for this case, the natural frequency is 300. Okay, now from the result that we had, we know that bandwidth is actually proportional to natural frequency. That is, the higher the natural frequency, the higher the bandwidth. That is also the reason why we was told that natural frequency of a second order system actually determine the speed of response of the system, which means the higher the natural frequency, the higher the speed response of the system. And this fact also shows when it comes to the definition of the bandwidth. All right. Now, So here I have larger bandwidth, larger natural frequency. Therefore, I have higher bandwidth. Okay, and this is section 2. As you can see, indeed, section 2 have larger bandwidth compared to the bandwidth of section 1, right? This is the bandwidth of P1. Okay, time is up. Okay, thank you again for your participations. Remember, only 2 weeks left for this semester. Let's keep up the good work.